All right. Good morning, everyone. Good to see you all here again. We're going to continue our journey on ordinary differential equations and understanding what they mean. Last time we left off talking about developing a formula for the population of lobsters. We're going to revisit that, but I want to get started with a quote. As I was digging up through my slides, I found for some reason I had this quote for my students at the time, and I think I remember why I put that quote in. But it's from the 30th president of the United States, Calvin Coolidge, and he couldn't summarize it any better. And it says that nothing in the world can take the place of persistence and determination. Talent or not, nothing is more common than unsuccessful people with talent. So if you rely only on talent, but you do not apply that talent, you're not going to do anything with it. Genius will not. Unrewarded genius is almost a proverb. Education will not. The world is full of educated derelicts. Persistence and determination alone are almost omnipotent. Now, I'm not saying you should not get an education, but you can have an education and be weak inside and never experience the opportunity that education could have provided for you because you just didn't have the persistence and determination to make it happen. So a degree does not make you successful, does not guarantee you a job, does not make you a better person. It is the journey along. Degree just gives you a credential, just says, hey, you know, this person checked all of those boxes. But success requires a lot of persistence and determination. And, you know, in the face of failure, one failure after another, you got to pick yourself up, bootstrap, and keep moving and keep moving. Because, and this has been my experience personally, that's the way to succeed and persist. Anyway, I hope this will motivate you that, you know, passing a class or not doesn't necessarily mean anything. But to pass, it's good to pass a class, but I want you to learn and understand what's happening. That's more important than getting an A. You could pass the class with a B, but have significant intuition and understanding, and your day is going to come where, you know, that understanding is just going to explode and boom, and you're going to do great things with it. All right. So last time we left off at this discussion of the population of lobsters, where we said in reality, because there's lobsters dying, there's competition for resources, there are predators, etc. In reality, a population of lobsters kind of looks like this. It starts at P0 with an initial population, and then somewhat grows exponentially, but then reaches a plateau where, you know, there's a balance between how many lobsters are joining or are being born in the population and how many lobsters are disappearing. And we designated that number K. You know, let's say you started with 10 lobsters, and then within that ecosystem, the ecosystem could not sustain more than 273 lobsters. Okay. Now, I had asked you last time as an activity to come up with a formula for this curve. And bottom line was that, you know, it's a difficult problem. There's no guidance to come up with this formula. I mean, like you could, you know, okay, I have this curve on, but this is a description. You cannot just come and fit a formula to this curve. I don't know what this curve really looks like. You know, what if the slope is further down or further up? We really don't know. We can't tell. And there's no rational mechanism to just come up with a formula for this curve. Okay. But I'm claiming that the formula for this curve is this guy. As a function of time, the population of lobsters as a function of time has this initial condition P0 times K, the maximum population, over this crazy denominator. And you might be saying now, how the heck did you get this formula? And that's what I'm going to show you. And that's what I'm going to show you, the power of ordinary differential equations or differential equations in general. But first, let's do a little warm-up, okay? So the approach we want to adopt is, instead of looking at the population itself and thinking of the population of the number of lobsters, we need to think in terms of the rate of change of the lobster population. How many lobsters are coming in? How many lobsters are leaving? And look at that rate of change over time, because that is easier to measure and think about rather than just the population, the absolute number of population of the lobsters in and of itself. First, we're going to start with a warm-up problem. Consider a population of lobsters with an initial size of P0. Okay. Now assume within that, so let's say you have 10 lobsters. Okay. Now assume that the birth and death rates for these lobsters are equal. So in other words, for every lobster that's born, one lobster dies. Okay. So exactly, there's a balance. So you always have 10 lobsters in the population. Now I want you to develop an equation for the rate of change of the lobster population over time. So lobster population P, I want you to come up with an equation dP by dt equal something for a population of lobsters that doesn't change over time. All right, take a minute to think about that, and I will see you over Zoom. All right, I'm back on Zoom. Take a moment, think about this problem now. We said that there's a population of lobsters that doesn't change over time. Okay, population of lobsters, let's call that P. Now I want to write a differential equation, and we always thought now rather than saying derivative, we're going to think a rate of change. So what is the rate of change of the population of lobsters over time if no lobsters are, if there's a balance, that population of lobsters is constant over time. So just write an equation dP by dt, so rate of change of lobster population equal what in this case?
0.
Yeah, why?
Because it's not changing.
Yeah, there's no change in the lobster population. If the number of death and birth, or if they're not having any babies at all, they're just, they live forever and they're just hanging out, having fun, there's no change. So dP by dt equal to 0. Does anyone disagree with Sydney? Okay, so I hope this kind of triggered something in your mind now as we take this up one notch. Okay, I'll see you on Zoom. All right, so just like Sydney said, in this case, the lobster population is not changing over time. So the rate of change, think of it this way, spell it out, verbalize it. The rate of change of the lobster population is 0, is not changing. And therefore, the equation in this case, dP by dt equal to 0. Okay, that's a differential equation for the lobster population. Now, this implies that as a function of time, P of t is equal to a constant, which is P0, the initial lobster population, as we had set out, to set up the problem initially. All right, let's take it up one notch now. And let's say that the lobster population actually changes at a rate R. Okay, so you could say that there is like one birth for every 2 lobsters, or like one birth or half a birth per lobster, or 0.25 per birth per lobsters. Now, clearly that rate multiply the number of lobsters, okay, gives you the total number of lobsters that are being added or removed from the population. So if we change the sign of that number, we can either add or remove lobsters from the population. But assume now that you are adding lobsters to the population at a rate R times P. R is a constant value, could be 0.1, times P, which is the current lobster population. So if you have 10 lobsters, you're probably going to have one lobster being created per unit of time. If you had 100, you're going to have more lobsters, right, being created. So that's why you multiply by P. So now develop an equation an equation for the rate of change for the lobster population over time, such that the rate of growth of this lobster population is R times P. All right. Take a moment, think about that. All right, I'm back with you on Zoom. To summarize, we said now this lobster population is changing, and that change is proportional to the lobster population, P. So if at any point in time you have a P population, then you're going to create R times P new lobsters. And that is the rate of change of the population of lobsters. So now what is dP by dt in this case?
Wouldn't it just be R?
Why?
I mean, if we're looking at it just RP and we're differentiating it with respect to P, wouldn't that just leave a factor of R?
Okay, so you're saying that dP by dt equal R, right?
Yes.
Yes, so that is not a wrong model, by the way. You know, you just developed your own ODE, but what does that describe? It describes a population where the rate of change of the population, dP by dt, is constant, okay? Where it's constant. What I'm saying is that actually in practice, the more lobsters you have, the more babies they're gonna make, right? Because they're more likely to interact and, you know, marry each other and make babies, right? But in your model, Sarah, you said, if I have 10 lobsters or 1,000 lobsters, they're always making 2 babies per day, for example. It might be true. It might be true for certain populations, okay? And it is not wrong. But for this specific case, and in a more realistic situations, you know, I'm not a naturalist, but, you know, I based on my readings of populations, typically populations grow proportional. The rate of change of the population is proportional to the population itself. It's obvious. The more people you have, you know, the more likely they're going to reproduce, right? There's more chance for them to reproduce. And so what would you, do you want to change that? Do you want to change your answer? What you did, Sarah, actually, you shouldn't differentiate R times P. You differentiated R times P, which is wrong. No, R times P in this formula describes the rate of change. So on the left-hand side of the equation, you should have rate of change equal to what? What is that rate of change? So who wants to amend the answer?
Does dP over dt equal RP plus P naught?
Y plus P naught. It is equal to RP, but why P naught? Why do you care about P naught?
Because that's where it starts at.
But you're thinking in terms of a formula. No, the d by dt equal RP already in it has embedded P naught, because if you remember your ODEs, when you solve for your ODE, what is your initial condition? It is P naught. So it will automatically have P naught brought into it. Remember, we don't care where we're starting. What matters is the rate of change of the population. How much it's growing. P naught has nothing to do with it, right? P naught should not have anything to do with it. It is equal to RP. So the rate of change of the population is equal to this factor R times the population itself. So it is dP by dt equal R times P, okay? Is it clearer now? The larger the population, the larger the rate of change, right? So if you had 2 people, they're probably gonna make, you know, 3 babies, let's say. Now, you know, if you had 20 people, they're probably gonna make 15. And then if you had 1,000 people, they're gonna make more, right? And so that rate of change is proportional to the at any time in time, at any point in time, the rate of change of the population is gonna be proportional to the population itself, okay? So let's see what that does. All right, so this was a good discussion on Zoom. Now, the rate of change of the population is proportional to the population of itself. So dP by dt is equal to some constant factor times the population itself. So at any point in time as the population is changing, the rate of change or the slope of that curve is proportional to the value at the curve itself. Now, the solution to this ordinary differential equation is P naught e to the RT. That's where P naught comes in. James mentioned P naught. Now, this is identical to the answer we obtained earlier, where we derived manually. We said, okay, the paramecium is going to double, or the lobster is going to procreate at R to the power T, etc. And we ended up with this formula. Well, this is another way of getting it. And this is actually a more elegant way. I know there's a little barrier early on about thinking about ODEs, but there's a point where it's going to click in your head, and you're going to find that this is easier to obtain than the previous methodology that we used. Okay, this is an easier way. It should be an easier way to think about things, because you're only thinking of rates of change, not the absolute number of the population. Okay, all right. So now we're going to take it up to the question that we were dealing with. Okay. Now, I want you to develop a differential equation for this type of population where there's competition on resources, there's predators, etc. And the population has a maximum carrying capacity of K. This is some number that is determined from experiments or observations or whatnot. Okay. Now, again, think in terms of rates of change. On the left-hand side, you always have dP by dt. But on the right-hand side, you have something. It's either growing, it's shrinking, it's constant, right? In this case, we want some sort of switch that says once the population hits K, there's no more rate of change. Okay, so as we are growing, once the population hits K, the right-hand side should be 0. Okay, so think of it this way. What would you change for R? We said that R is a constant. Okay, now replace R by R times something minus P. That's your switch. Okay, so in the previous example, we had dP by dt equal R times P. Now we want R to switch so that initially it's just growing as if it would grow normally, but then when it hits K, it's just going to go to 0. All right, so take a moment, think about that. Again, you're only changing the right-hand side. The left-hand side, we know it's just rate of change of the population. Okay, so let's go over Zoom and discuss that. So I gave you a hint on this slide. I told you replace R, that growth rate, which was constant before, by some, and make it not constant, make it a function of the population such that it kind of switches off when we hit K, okay? When P becomes equal to K. So what would you do, and what would you change in this formula? So we still have dP by dt equal R times P. Now we're going to change R and make it R times something minus P. Now that something needs to be 0 when P equals K. So what would you put in the question mark? All right, so I got a lot. I do not see your chat. I can see some chatting. Just speak up. Feel free to speak up. Got a bunch of people.
K.
Okay, Sydney. That's your second answer today. I'm gonna say if that's right or wrong. Who else? Who disagrees with Sydney? So Martha and Carson, they said K, right?
I
Martha?
agree with Sydney on this one.
Okay, you're all teaming up against me.
K.
Abby is okay. So who would you want to elaborate a little bit? Your answer is correct. The right side is going to be R, some constant, times K minus P times P. We're still multiplying by P because the growth rate is still proportional to the population itself. But what happens with this K minus P switch? What happens? Do you want to talk about it, Marta, a little bit?
I mean, that at some point that might equal 0, and then you don't.
When will it equal to 0?
Growth. When K equals P.
When P equals K.
Or P equals K.
Yeah,
sorry.
because P is changing, right? So initially, when the population is small, right, K is a fixed number, but then P is very small. So you only get R times K times P on the outside. I'll explain this on the slide. And the population is going to grow nicely, just as it would normally grow, okay? But then as P approaches K, that coefficient starts shrinking and it starts normalizing the curve to flatten it out, okay? I'll explain this on YouTube. All right, you guys are nailing this. Okay, here's the way we do it. Okay, so dP by dt is always thinking rate of change of the population of lobsters. We know it, in practice, all populations grow by this form. dP by dt equal R times P, where R is some growth rate. Now, in the previous example, we thought of R as a constant, but now we're gonna change that R. What if we say, instead of R, this is gonna be a constant times K minus P. K is what's called the carrying capacity. It's the maximum number that the population can reach, okay? And I'm claiming that this is actually gonna be a switch that makes the population settle down once P reaches K. So think of it this way. What happens initially when the population is small, okay? And what happens as the population grows and approaches K? Initially, when the population is small, this P, and this P is small, but more importantly, this term K minus P is dominated by K. Because P is so small, K is clearly a much larger number than P. So what you get is almost behavior like R times K times the outside P, okay? Now R times K is a constant, so you get exponential behavior initially when the population is small. Now as P starts increasing, this term starts approaching 0, because as P approaches the value of K, so let's say K is 1,000 lobsters, okay? You start with P equal 1, 1,000 minus 1 is 999, times 1, you know, that's gonna keep the population growing exponentially. But as P approaches 900 or 980, K minus P becomes a very small number. And the entire right-hand side becomes a small number until it hits 0. And when it hits 0, the rate of change, not the population becomes 0, the rate of change becomes 0. And then the population just flattens out. Just do it this way, just flattens out, okay? And this is how I obtained this formula. So instead of thinking of the formula itself, we thought of an equation that gives us a formula. We thought of an equation whose solution is the formula in question. Now that equation didn't think of the population itself, it thought of the rate of change of the population, which is a more powerful way of thinking. This really revolutionized, this way of thinking is what revolutionized science. It is when calculus was brought in, you know, with Newton and how to think about physical systems. Rather than thinking of the individual values on the system, you think of the rates of change. And this truly revolutionized science. All right. So there's reason behind all of this madness. And this is just to make the point that ordinary differential equations are important. So we're going to make these two distinctions here. It is generally much easier to relate rates of change of quantities than it is to develop algebraic formulas for quantities. So again, think of the population. We had no clue on how to proceed with developing a formula that flattens out. Some of you said, oh, we switch it. But you know, is this realistic? It's not realistic. There's no physical, rational reasoning behind that. But when we thought of the rate of change, we said, well, we know populations grow as R times P. And then what if R just turns into a switch and you do it smoothly and continuously, just like we said. So the solution to a differential equation is a function, while the solution to an algebraic equation is a number. So when you have a formula, the answer to that formula is just a number when you plug in everything. But when you have a differential equation, the answer to that differential equation is a formula which you can use then to get numbers, okay? And that's how you develop formulas and you become famous, okay? Now the function, like I said, that results from the solution of a differential equation usually serves as the algebraic relation that someone else can use and get specific numbers. Okay, so this entire detour about, we're not interested in, I mean, population dynamics are very interesting in and of their own, but their behavior mimics all systems we see in engineering, and you'll see in kinetics specifically. It's the same thing as a new chemical species are created and destroyed and consumed and changing. You know, it's the same thing as a population does. Okay, but the point to drive home here is the importance of differential equations and their distinction from algebraic formulas. All right. Now I want you to take a moment and do a paradigm shift in your brain and give me some examples from daily life that you can think of that have rates of change in them. Okay, just things you see in your daily life. You know, maybe you're driving. Sometimes you go fast and slow and fast and slow. You know, yeah. Give me an example that has rate of change from real life. All right. Come on, let's have it. Some examples from real life about rates of change. Floor is open.
I noticed that throughout the day, my motivation changes when it comes to doing homework.
Your motivation changes over time. I agree.
Yes.
But Abby, the answer to that is persistence. Motivation is an emotional response, right? It kinda, but if you rely on that too much to drive you, it's gonna ebb and flow, right? It's gonna have a crazy rate of change. But persistence has a rate of change of 0. You're persistent all the time. You just get things done all the time. All right, good example. Others?
My internet speed.
It changes over time.
Yes.
All right, Carson, you have something. Let me see if I can open up the chat window. Okay. Would the rate of change with the change in specific heat capacity of what? Growing vegetables, the rate of change of the size of the plant, interest rate on student loans. Well said, Weston. Well said. That's great. Amount of traffic. Yeah.
How hungry I get.
Yeah, and that changes over the day, right? Yeah, think of rate of change. Student grades this semester. I sense there's a message being sent to me in this in this comment. But yeah, your grade changes.
To be fair, Professor, I wasn't talking about you specifically. I just mentioned general.
No. Don't worry. Yeah, but let's think of more kind of physical things like you know, rate of change of temperature during the day, right? As the sun rises, you know, the temperature is going to increase, right? Because there's more heat coming in. So that change in temperature is a function of how much heat is coming in, but it's also going to be, you know, there's going to be competition to reduce the temperature, you know, if a cloud cover comes in or as you go through the night, right? So there's a rate of change. Snow melt, snowfall. Good. Yep. All of those are great examples. Okay. That's great. All right. Good. Now you're thinking in terms of rate of change. Let's continue on YouTube and see where we move on next. Okay. All right. So those are all great examples. Everything has a rate of change in it. You're driving, the water flow, the electricity usage, the internet speed, your interest rates on student loans, like Weston said, and a bunch of other examples. All of those are all interesting examples. Your movement, your position, your velocity, your acceleration changes with time. Now think in terms of rate of change from now on. Don't think in terms of the value itself. Think in terms of what is causing my change in my speed. So the rate of change in my speed is going to be affected by my gravity, by the drag, etc. And that is a much easier thing to express rather than thinking of the acceleration or the speed itself. Okay. One great example that we're going to work on, and that is related to current events, are pandemics. So rate of infection, rate of people visiting different states, rate of vaccination, all of those things are very important numbers. And you can measure the rate better. You can model the rate, okay, easier than you can model the actual numbers themselves. All right. Okay, so now let's go on and do some definitions. I know this might be a little bit boring, but I need to get those out of the way. So please bear with me, and then we're gonna do a few fun things. We're gonna cook a lobster or an eggplant, and then we're gonna together model a pandemic using ordinary differential equations. And I think this is gonna be a great example to finally set the idea of ODEs in your mind. Okay, so we classify differential equations into two general categories: ordinary, partial. Okay, ordinary differential equations, or ODE, is just a differential equation. We said a differential equation is an equation that has derivatives, rates of change in it, relates rates of change. Okay, now that differential equation could be ordinary. It's ordinary if it only has one independent variable. This means that an ODE can contain only ordinary derivatives, and hence the name ordinary differential equation. The population growth is an example of an ordinary differential equation. You only have one independent variable t, okay, and you have the dependent variable, okay. The rate of change of height in a bucket of water, where you're bringing in water, taking out water, and this is the formula for the rate of change of the height of water in the bucket. The heat equation, heat advection equation, we're going to talk about this a little bit later. So this is another example of an ordinary differential equation. Now notice, this is the first derivative, second derivative. The order of the derivative doesn't matter as long as it contains only one independent variable, okay? Some of those are with respect to time, and some of those are with respect to space. We'll discuss those in a minute. Partial differential equations, on the other hand, describe differential equations that contain partial derivatives. When do you have partial derivatives? When you have many independent variables, things that change with time and space. For example, fluid mechanics, fluid flow. Flow could move in either this direction, that direction, up or down, and it can change over time as well, okay? It can change the value over time. So that's an example of a partial differential equation. And this steady state heat equation, what's called, is an example of a partial differential equation. You have two independent variables, x and y, and you see the partial derivatives over there. This is another equation that combines time and space. Space is described by x, time is described by t, and this is the unsteady heat equation, okay? This is the unsteady heat and diffusion equation, okay? Also, a partial derivative has time, space, and space over here, okay? And it has different order derivatives, all right? So we're not talking about order yet. Now, we're going to focus on ODEs because that's the subject of this chapter. Okay, we're going to classify ODEs into two types of problems: propagation or initial value problems, and equilibrium or boundary value problems. As you've seen in the previous slide, in the ODE column, the ordinary differential equations column, we saw equations that had time in them and saw equations that had space in them. There's a distinction between the two. Whenever you have time, typically this means a propagation type problem or an initial value problem. In other words, what those equations describe is, given the initial state of a system and knowing what external forces are going to affect the system, look at the evolution of the system over time. So the ordinary initial value problems are typical problems of populations, or of other examples are like well-mixed systems that we study very well in chemical engineering. You have a mixed system, you put in an initial solute and reactant, or put in a bunch of chemicals and say go, and they start reacting over time. But everything over the entire bucket or the entire domain, everything looks the same, okay? So that's why there's only change over time. We call those initial value problems. Filling or emptying a tank, population growth, pandemics, disease spread, etc. Those are all examples of initial value problems. You start with an initial condition, the recipe of how that initial condition is going to change based on the rate of change of the unknown quantity, and you move that over time. Now, the other side of this equation or the classification of ODEs are equilibrium or boundary value problems. So those are problems that describe the change of something, but that is bounded within a certain boundary. A great example of this is heat transfer. So, you know, it's very cold outside and it's warm inside. You go, you touch the wall on the inside of your house. It's nice and warm, looks like room temperature. But then you go outside and you touch the wall and it's very cold, right? Now, between those 2 points, there is a change in temperature. And we did that example early on when we did linear systems of equations. This is where this comes from. This is the heat describes, this is an example of the heat equation that describes the change in temperature between the inside where you have the sheetrock and outside where you have your siding and it's cold. And you can understand the temperature change in here. Maybe you're thinking about changing the insulation. You want to think about what type of insulation you want to put to reduce the effect of the outdoor temperature on the inside. Okay, that's a boundary value problem. It's bounded by the temperature on the inside and the temperature on the outside. Other examples in engineering, the curvature of constrained beams, or for example, when they hang the electric cords, like those huge from Rocky Mountain Power. I don't know if you've seen them. Go on YouTube and like Google, you know, hanging of power lines. This is a huge process, and the tension on both ends dictates the shape of the curve of that cord. Okay, so that's a boundary value problem. Spring mass systems are other examples, but you know, guideline, whenever you see T, time, okay, initial value problem. Whenever you see space, boundary value problem. Now in this course, we're not going to derive those equations. So I will give you those equations, but I want you to at least understand what they're doing, okay? But I'll give you the equations. Later on in your career as chemical engineers, you're going to be able to develop equations like this on your own, okay? All right. Now, initial value problems typically require initial conditions. Obviously, you want to start with a certain number of population, or you want to know what reactants you have in your reactor. And boundary value problems require knowledge of your boundary conditions. All right. Now, one more classification of ordinary differential equations is the order of the ODE. Now, you noticed we separated the ODE in time and space, okay, so initial value and boundary value problems, but we didn't talk about the degree of the derivative, okay? Is it a first derivative, second derivative, third derivative? All of those are possible. Now, to simplify nomenclature, we say a first order ODE contains only the first derivative of the dependent variable. And it could come in a single equation, d phi by dt equals some right-hand side, or d phi by dx equal some other right-hand side, okay? This is a boundary value problem. This is an initial value problem. Or it could come in systems of equations, you know, written here as a vector, d phi by dt, vector phi, contains multiple variables. We're going to see the pandemic as an example of a system of equations. But those are all first order, okay? And same thing for boundary value problems. You can solve a bunch of equations together. A second order ODE contains second order derivatives, but also potentially first order derivatives. You know, examples are the advection diffusion equation, steady state. It's still an ODE, but it has second and a first derivative, okay? Now, this equation describes this. I don't know if you remember your cartoons, but there's always this cartoon of Tom and Jerry. I grew up with Tom and Jerry, and there's always the lady who owns the house. She's baking a pie, and she puts the pie, and there's this smell of this delicious pie that grabs Tom, and he flies off smelling the smell. Okay, so the mechanism that moves the smell of the pie is what we call advection and diffusion. The air clearly moves the smell towards you or Tom and Jerry, and also the smell diffuses in air. You learn in your career what diffusion and advection means, but typically advection means there is airflow that is moving things with the air and with the velocity of the air, and diffusion means communication at the molecular level. Anyway, but this is the equation that describes this phenomenon, okay? All right, Now, an example of systems of equations that we will actually do together, we're going to solve this system of equations together, one example is how to model a pandemic. In this case, we're going to go in detail, much detail about these curves, but what this model does, it looks at three populations. The susceptible population, that's those of us who have not been infected yet. Okay, we are susceptible to be infected. Those who have been infected and those who have recovered. Okay, so clearly susceptible, when they interact with infected people, they get infected. But the infected people, as they recover, as they go through the illness, they eventually recover. And this system describes these three curves. Initially, you have in the blue curve a healthy population uninfected, and you introduce maybe one infected person. And then as the susceptible population interacts with the infected, 1 or 2 or 3, the number of infected people starts rising, and it starts consuming the number of susceptible people. Okay? And then as it reaches a peak, those who are infected, they start getting recovered in this green curve, okay, and until everyone is recovered. Now, when we talk about flattening the curve, you probably learned what that means. This is what this means. It means this peak over here, how high do we want it? Do we want it to cover 60% of the population, 80%? Is 20% of the population acceptable? Is 10% acceptable? Should we go to 0, those are the questions that epidemiologists and decision makers and all of us have to consider. We're going to dig deeper into this model together. I hope you'll have fun with it, and then we'll develop our own model where we introduce social distancing and see how much social distancing is going to affect the curve. Remember, the goal was always to flatten the curve, not make it 0, because clearly that's an undoable thing. It's like saying to prevent car accidents or car wrecks, we're gonna prevent everyone from driving, right? That's a ridiculous thing to say. Anyway, okay. Now, why do we need numerical methods to solve ODEs? If it's not obvious to you, it's because these ODEs can be really complicated and difficult to solve. You cannot have analytical solutions for those. Think of the pandemic model I gave you. There's no way you can come up with an analytical solution for that. The equations can be highly nonlinear and coupled with each other. Forget about it. That's where math comes in and helps you kind of try to find analytical solutions for some ODEs. But in this course, this is where we differ from math. We're going to take the ODEs and just always solve them numerically. Okay. Now, we will do maybe a few case studies where we know the analytical solution and compare our numerical solution, but we're going to be just enjoying our time doing solving these equations numerically. And therefore, there's an immediate need to study ordinary differential equations numerically. I had to say this. All right. We are going to start with initial value problems. So far, we've categorized differential equations into ordinary and partial. And then we said ordinary differential equations, they can be classified into initial value and boundary value. They can be first order or second order. Okay, we're going to start with initial value problems first. These are equations of the form d by dt equals something on the right-hand side with an initial condition. That's all you need to properly describe an initial value problem. And the first example we're going to do together is cooking a lobster. Now, if you are a vegetarian, you can substitute in all that precedes, you can substitute the lobster with an eggplant or some other vegetable. And here's the story. Here's the setup of the story. Okay, there's going to be hopefully some humor in here. But assume that a recent report found that the population of lobsters is growing out of hand, and that those lobsters are eating everything at the floor and disrupting the global ecosystems. There's volcanoes erupting, and like the shrimp population is dying off, and is disrupting everything. And then the WHO and the CDC, because they have control over the world and what we do, they started asking people to eat lobsters as snacks throughout the day. Like, eat as many lobsters as you can, go and fish for lobsters and eat them. so that we can control the population. Now you can substitute lobsters with eggplant, like I said, eat as many eggplants as you can. I actually really like eggplants. We in the Mediterranean, we actually just cook them and do the baba ganoush. It's really delicious treat. Maybe I'll give you the recipe one day. But anyway, so these are clearly, a way to control the population. Now you are now, as an engineer, you are tasked with finding out the fastest method to cook a lobster. So clearly, we need to pick up those lobsters and cook them as fast as we can, so that we can give them to people so that they can eat them. Okay. And as an engineer, you're tasked with this task, and you have two options looking at the cooking the lobster. You could either boil it in a liquid, could be water or oil, like deep fried lobster, or bake it in the oven. Okay. It's interesting that you can deep fry everything. When I was at Tennessee, I went to one of a car crash derby once, and they were like deep frying everything. Everything was so delicious. They had these funnel cakes with the powdered sugar on it. I was like, deep fry it more. I told the guy, deep fry it more. It's so delicious. I want more of the oil. So anyway, you could deep fry the lobster, or you could boil it in a liquid, or you could bake it in the oven. Okay. Do you know which one is faster? We don't know. Well, that's going to depend, right? Okay. So that's the question. Should we put it in the oven or boil it in water? Now let's make some assumptions, and I will help you develop. We're going to develop the ODEs together, and then we're going to hop on to Python and solve the ODEs to figure out which one is going to be faster, which method is going to be faster. So we first assume that the cylinder, or that the lobster or the eggplant can be approximated as a cylinder of length 30 centimeters and radius 10 centimeters. It just came up with those numbers because they just work. Okay, and assume that the lobster remains at a uniform temperature. That's important, and that's actually, I think, is a reasonable assumption, especially if you're like deep frying. So initially, the lobster might have different temperatures, or it actually might be at all of it at room temperature. You put it in the water or in the oven. Initially, the outer surface is going to heat up faster than the inside, but that causes a change in temperature inside the lobster, and that makes the problem not initial value anymore. So we're going to assume that the lobster is entirely at an initial temperature, and we're going to move that temperature of the lobster as we change in time. So clearly what we're after here, cooking the lobster, means getting it to a certain temperature as fast as possible. Okay, let's say cooking temperature 400 degrees, okay, Fahrenheit. The lobster's mass remains constant with time, so we don't want to worry about that. And this thing in heat transfer, the heat capacity is approximately that of water. It's a great assumption as well, because the lobster is mostly made of water. Okay, now these are some parameters. Don't worry about those. They're going to be pre-programmed for you in Python, and they'll be given to you. But the point is that there are two ordinary differential equations of the type of initial value problems, for these two mechanisms of boiling the lobster, of cooking the lobster. If you boil it in water, it's called the convective heat transfer problem. This is the governing equation for the temperature of the lobster. It's the rate of change of the temperature of the lobster with time is equal to something over here. Minus HA over MCP. H is what's called the convective heat transfer coefficient. H is going to be higher for oils than it is for water, than it is for air, for example. And we talked about this a little bit earlier in the class when we were doing the heat transfer equation. Okay, so that's H. It tells you how fast you can move heat from the liquid to the lobster. A is the area of the cylinder, the cross-sectional area. The surface area of the lobster. M is the mass, and CP is the heat capacity. So don't worry about those. Those are just a constant. We can change them. Okay. Now, what's critical here is if you can change H. H tells you how fast the liquid is heating the lobster. So if you air fry it, H is going to be a very small number, so it's going to take longer to cook, versus putting it in water versus putting it in oil. H is going to increase as you go towards oil. So oil will be more effective maybe, but there's this other parameter here called T infinity. That's the temperature of the liquid, whether you're heating it in the air or boiling it in the water or boiling it in the oil. So oil is going to boil at a higher temperature, so T infinity is going to be higher, so that difference is going to be a little bit higher, so you can probably cook the lobster faster in the oil. T is still the temperature of the lobster. So rate of change of the temperature of the lobster is this thing, okay? And as T increases, now this is similar to the problem we solved with the population. When T approaches T infinity, that's it. We're going to stay at T infinity because it makes sense. You cannot heat the lobster to a temperature higher than the liquid it's bathing in, right? So if the liquid is at 100 degrees C, then the lobster's maximum temperature is going to be 100 degrees C. Cannot go higher than that. Baking it in the oven has a slightly different equation. It's still a rate of change of temperature. Let me see if I can do this correctly here. It's a rate of change of the temperature of the lobster over time, okay? But on the other hand, you have a bunch of parameters over here. In this case, in the oven, they're mostly constant. We can't change any of those coefficients over here. There's sigma, constant, and the emissivity, and a bunch of other things, the area, the mass, and the CP. But what you notice here is this fourth power of the temperature. So this equation, the right-hand side, almost looks similar to this one, but from what we know about heat transfer in the oven, which is of the radiation type, where you do not have contact with the heat source, you just turn on the heat source and it radiates heat towards you, we see that the change in temperature is T to the fourth on the right-hand side. So this might significantly affect how fast we can cook the oven. No, we can cook the oven. We can cook the lobster in the oven, okay? We're gonna look at both of these options and we're gonna play around with the parameters a little bit. Here we can change H. So in other words, changing the medium in which we are cooking the lobster. We can change T infinity, the temperature of the medium, air, water, or oil, or whatever. And over here, we can change the T infinity. That's the temperature of the oven. Are you broiling the lobster? So you put the temperature at, whatever, 550. That's the broiling temperature, or you put it at 350 to bake the lobster. So we're going to look at all of those options, okay? Now, we know the ODE, we know the governing equation. We're going to learn how to solve it now. But first, we're going to do it in Python. But the general strategy is as follows, okay? Before we start digging into the nuts and bolts of what's going on, I want to give you a flavor of how fun it is to solve ODEs and how important they are. So the general strategy is that we start with an initial condition. At T0, we know the initial condition. In our case, for the lobster, we know the initial temperature of the lobster. And then we're going to go over time until some end time. Let's say, we're going to run this model for 2 hours and see what happens. And then your goal is to find this curve. We don't know what this curve is, okay? We only start with an initial condition. We want to get to T end, but we don't know what this curve is. We don't know what it is, right? That's the answer. So what we're going to do, we're going to divide our time interval, our time domain, into small intervals. We call this process discretization, just like we did early on in linear systems, where we discretized the rod into small sections in space, okay? Over here, we're doing this in time, okay? This is the time domain, okay? And all T0, just designate each point on this time interval as, give it an index. This is T0, it's equal to 0, really. T1 is T0 plus this spacing, and then T2 is T1 plus this spacing, and so on and so forth. Assume for simplicity that the spacing is constant, okay? That we have a fixed spacing in time. Now we call this the time step size, delta T, or H for simplicity. Okay, this is the size of the time step. And we're gonna start now with phi 0, and then we're gonna develop a formula to predict the value of phi at subsequent times, okay? So from phi 0, we're gonna go to phi 1. Clearly, there's an approximation involved, but we're gonna be inspired by the ODE itself, okay? Because we have the recipe for the ODE, okay? And that's the procedure. That's the general idea of how we're gonna do this, okay? But first, we're gonna do it in Python so that we can see the full power of all of it and just use built-in Python functions, and then we'll dig in and see what Python is doing under the hood, okay? So starting with Python, turns out that scipy.integrate provides a library for solving ordinary differential equations called ODEint. That's the same name, I think, as in MATLAB, okay? Now, ODEint sorry that some of the items are missing here. I will readjust before for next time, but the PDFs will contain everything. What this says here is ODEint solves an ODE of the form. Okay, give me a moment. Let me fix this and I'll be back with you. Give me a moment, please. All right, I apologize about that. My slides were, I was changing from a widescreen to a standard size slide and some of the text was chopped off. So this should fix it now. So ODEint solves an ODE of the form dy by dt equal to some right-hand side function of y and t. Now remember, our right-hand sides could be a function of the dependent variable, could be a function of time, both, and other things. But most importantly, they might be a function of other constants, but that doesn't matter. So that's why we only write right-hand side function of y and t, okay? And this function signature is simply ODEint. It takes a right-hand side routine, takes an initial condition, and something called t. So let's understand what those are. RHS is simply a Python routine that implements the right-hand side of the ODE. So it just implements RHS of y and t in that order, okay? That's what it does. So for example, for the cooking the lobster in a fluid, the right-hand side is going to be minus HA over MCP times T minus T infinity, okay? That's what it's going to be like. It's just simply a routine. Y0 is your initial condition, and T is simply an array of points at which you want to find the solution. So this T is nothing more than those points that I described on the timeline that I showed you earlier. And this can be done very easily with a linspace. You know Y0, you define the function routine for right-hand side, you call ODEint, and you get a solution, okay? Now the right-hand side, you can just simply define it as def right-hand side, y and t. Now, once you go into the right-hand side, you will assume that you have access to the value of y and access to the value of t. So you just use them as if you're just writing the equation of the right-hand side, the formula for the right-hand side. All right, we're gonna do this together. I want you to go and download from the modules on ODEs, from module ODEs, I think it's called, on Canvas. Download the lobster example with gaps, okay? And we're gonna work on this together, okay? All right, I am back on Zoom. Now you can work with me on Zoom, okay? Let me see, Zoom meeting. This is the Zoom meeting. And I'm gonna share my screen now. You can just follow with me on Zoom, please. I'm gonna share my screen. Let's see. Yeah, I hope you've downloaded the notebook. So, I expect that you will go through the notebook and understand what's happening and what's going on, read some of the descriptive text on top of what we're doing together over here, okay? All right, I'll give you a few moments to make sure you get that notebook. Who's still
Professor,
working?
is that the notebook that you've submitted into our files? Because when I downloaded that lobster example, I got the 2020 version, I believe. I don't see the same screen that you're looking at right now.
You don't see the same one that I'm looking at? Okay.
I don't.
Okay, what are you seeing? Let me
It looks like
double
yours
check.
is already filled in.
Mine is already filled in. Oh, no, it's not filled.
Meaning,
Oh, you probably have a bunch of other question marks. Okay. Okay, that's okay. Let me yeah, is that the only difference? Let me see.
no, mine doesn't have any of that L or A or anything like that. The A equals, R equals, I don't see any of that information.
Oh, the text you mean over here, the text? You don't see any of that? Okay, so let me download, give me a second, please. I'll update it. It's probably something that I changed after the fact.
Mine does have all the text, and I downloaded it from files, so I don't know.
Oh,
was it under ODEs? Because the only one that I see for the lobster with gaps, it was from April 9th, 2020.
So if you go under modules, yeah, I'm not sure. Yeah, it is the same file as the one I used last year, and that was transitioned from last year. Who's having the same issue as Braden?
Me too, brother.
And Dylan. Okay, so if you go to Files, Jupyter Notebooks, ODEs, and lobster example with gaps, that's the one, April 9, 2020. I'm gonna download that. Okay.
Professor, I think the stuff that Braden is referring to that he's missing are the variables that are defined below. Not the upper text is, I think, here for everybody, but it's the define RHS CONV.
Oh.
You have a lot of information there. Same with RAD. I don't have any of that information. There's like 2 lines with just mostly question marks.
Oh, okay, because it's with gaps, so we have to fill it together. Okay. Okay, that's yeah, that's the difference, because you are supposed to fill this, we are supposed to fill this together. It's just the one that I have here is already pre-filled, like I think Marta was saying. So, or okay, so let me get that over here. Downloads. Okay, so good. We're in agreement. So Sam, that's you said we have the same one, but you're still missing the functions. That's for you guys to fill out. Okay.
Okay, that must have been the issue, Professor. I thought that all of those things.
No, sorry, that's for you to fill out. I just had a different version.
Was stuff that you had.
That's okay. That's okay. Okay. So this is the one you would be seeing over here, right? That's the one you'd be seeing, right? That's the one you're seeing, Braden?
Yes, that's the one that I'm
so
looking
the
at.
question marks, yeah, that's exactly the same one. The question marks are for you to fill out, okay? So I need a way to share with you the slides now. Okay, let me move my slides to the shared screen. And I want you now to try to fill in the gaps over here for the first model. Okay, so let's first execute that first cell, just boilerplate stuff, NumPy and Matplotlib, etc. Just execute that. Okay, now the first right-hand side we want to define is the right-hand side of boiling the lobster in water. If you can see my curve clearly. So it's going to be minus HA over MCP times T minus T infinity. And those are the numbers over here. So go ahead and just start filling in the gaps so that your right-hand side looks like minus H times A over M times CP, right? Times T minus T infinity. Okay, that's your right-hand side, correct? So we need all of those parameters to be in. Okay, so go ahead and start filling out those quantities, please. Whoops. Did it switch back to the other one? Lobster example. Okay, this one. My computer becomes exceedingly slow when I'm sharing and recording on Zoom and
Professor, there's a question in the chat asking you to zoom in a little bit on the Jupyter notebook.
on the Jupyter notebook.
Yeah.
Okay. Is this good? Sorry, guys, I cannot keep up with the chat. So please speak up. Otherwise, I'm not going to see your comment. Now, don't go later and say in your review that Professor Saad was not answering our chat. I mean, there's no way I could see everything here in front of me. So please speak up if you have a comment. Okay. Thanks, Abby. All right. So who wants to help me fill in the gaps? Braden, do you wanna take care of that?
Sure, I could give it a shot.
Go ahead.
So I started off by putting that L is equal to 0.3,
Mm-hmm.
R is equal to 0.1.
Mm-hmm.
Then I typed out that area equation of A equals the 2 pi RL plus 2 pi R squared.
Mm-hmm.
And then our M is equal to the 1 kilogram.
Mm-hmm.
Then our CP is that 4,200.
Mm-hmm. And what about H?
Then H is going to be the 500.
Yep, perfect. And then this is our right-hand side, correct? Minus HA over MCP times T minus T infinity. So we still need a T infinity. So T infinity is simply 374, okay? That's the temperature of the fluid in which we are cooking Mr. Lobster, okay? Okay, good. I agree with that. Anyone have issue with this? Has issues with this? Now, pay careful attention. Whether there is time on the right-hand side or not, whether there is the dependent variable on the right-hand side or not, when you're using the built-in Python function odeint, your function signature for the right-hand side always has to be of the form right-hand side dependent variable, independent variable. Okay. Always. You could call this y if you want, but then you would have to change over here. You'd have to call this y. I say it's just easier to keep your nomenclature that you started it out with for the equation. All right, let's do this for radiation. Who wants to take this? So clearly the area for radiation is the same. So I'm just going to copy L, R, and A, and M for the mass, and actually CP. I'm just going to copy them from up there, right? Because those are the same quantities. Okay. I still have sigma and epsilon, right? So if you look in the slides, if you look at the equation, it's dt by dt minus sigma epsilon A over MCP. So I need a sigma, which is equal to 5.6704 e to the minus 8 joule per meter squared per Kelvin per second. And then epsilon epsilon is equal to 1. And then the right-hand side for baking it in the oven is going to be minus sigma times epsilon times the area over m times Cp times t to the power 4 minus t infinity to the power 4. Okay. Now, this is going to be a different T infinity than the other one, because in the radiation environment, you can set the oven to much higher temperatures. When boiling it in a fluid, the fluid sets the maximum temperature it can change phases at. Okay, it depends on the altitude and the type of fluid you're looking at. So water boils at 100 degrees. At my house, water boils at 98 degrees. And actually at 94 degrees. And that's why there's books about cooking at high altitudes. When my mother-in-law came and stayed with us, one day she was making us this delicious spaghetti, and she was like, there's something wrong with your oven. It's not cooking the spaghetti well. I was like, yeah, that's because the water boils at a lower temperature. So the spaghetti is gonna cook slower than it would cook at sea level, for example, because the maximum temperature of her is going to be lower than it would be at sea level. Okay. Okay. So now we've defined.
Professor?
Yes. Who's speaking?
How come we're calling time if we don't have that anywhere in the function?
Who was that?
James.
Oh, James. Okay. So that's a good question. This is a placeholder. Now, the way this is going to work, ODEint internally is going to keep calling this right-hand side. Is going to go and say, okay, now I'm integrating in time. At this time level, I want you to calculate the right-hand side with this given temperature and this given time, because ODEint knows the time as it's moving in time, right? It knows it's going, I'm going now from T0, now I'm at T1 and at T2. And by default, ODEint assumes that your right-hand side in general is going to be a function of both your dependent and independent variable. So it assumes that you always have that format, that function signature. Now, whether you use it or not doesn't matter. So time is going to come in to the formula, but we're never going to use it. So what? Make sense?
Yeah, thank you.
Yeah. Okay. Once we derive the formulas for how Python is doing it, it's going to make more sense for you. Okay. So now go ahead and execute right-hand side convection, right-hand side radiation. Now, over here, okay, forget about this. Over here, what I've done, I've already, okay, neglect these cells, please. Neglect these cells. Let's just go to this cell over here using Python's ODEint, okay? From SumPy.integrate, import ODEint. Now I want to run this for 20 minutes, okay? But time in the standard, when we're deriving ODEs, etc., is going to be in seconds. So I need to define my end time in seconds. So I multiply 20 by 60 seconds, okay? So that's 20 minutes times 60 seconds per minute, okay? And then I create a linear space for time. That's what we said when we developed when we talked about the formula for ODEint. Okay, that formula required an array for time. That's it. That's how I created. I'm going to start from 0 to t end. Okay. Now by default, it's going to make 100 points. I'm not going to worry about that right now. We can increase the number of points. We can decrease it. That's a different question. But right now, just do it like this. Our initial condition is 311. That's a slightly cold lobster because I assumed I took it out from cold water. Okay, at Red Lobster. And now here's what I'm doing. I'm going to call ODEint for the convection problem, and I'm going to give it the right-hand side for the convection problem. So what did we say ODEint takes? So let me show you the slides over here. ODEint takes at least these three arguments: right-hand side, y0, and t. So what am I going to put here for convection? It's right-hand side, convection. And that's all you need to put the name of the right-hand side. Because internally, Python is going to go and call that name and pass it any parameters it needs to pass it. The second argument is going to be the initial condition, which is simply T0. And the third argument is going to be the time array over here, time. Same thing for radiation. I'm going to call ODEint, but in this case, I'm going to give it the right-hand side radiation function, or the oven, okay? And I'm going to give it T0, and I'm going to give it time. And you execute. And it gives you an error. All right, so let's see. T infinity is not defined. I had a typo over here. Okay, so T infinity is equal, let's say, 400 degrees. Sorry, we forgot to define T infinity in the radiation right-hand side. Okay?
Should we keep T infinity the same in both of the functions? It's like 374?
No. Well,
No, doesn't.
not necessarily, because you can, let's try that. Actually, that's a good point, Abby. So go ahead and try that. So let's try that next. Let's do this right now. Let's say you're baking it at 400 in the oven, and in the liquid has a heat capacity. The H, convective heat transfer, is 500. That's probably good for water, and that's 374. And this is what you get. Are you getting this first? Are you getting this plot in your notebooks? Great. What are we looking at? On the y-axis, we're looking at the temperature of the lobster. And on the x-axis, we're looking at time. And that's not in seconds, it's in minutes. Okay. So we're looking at time in minutes. So clearly in this case, the boiling is going to be much faster than baking. Because look, we achieve a temperature of whatever, 374 within 2.5 minutes for the lobster. Then with the oven is shown here in orange. Okay. Okay. So what do we do next? We have a lot of parameters to play around with. If we focus on the fluid, on boiling or heating in air, we can manipulate the heat capacity over here. So let's say you want to fry it in air. Air has a very low heat capacity. So let's say we put 0.1, not heat capacity, sorry, heat transfer coefficient. Let's say we put 0.1 over here. Go ahead and run everything again. See what happens. Now, if you put it in air, it's probably never gonna achieve a high temperature. It's not enough. Okay, so maybe we make the air hotter. Let's make the air, I don't know, let's make it 800. So you go and change the T infinity for the convective case to 800. And run this again, and let's see what happens. It nudged it a little bit, but not very much. I see a lot of faces squinting. Maybe we should stop here and continue next time. What do you think? But we're going to have to pick up from here next time, okay? But at least now we solved the ODE. I want to do what Abby suggested first. So I'm going to switch back to a advection heat transfer coefficient to 500, 374 for the liquid, and 374 for the oven, okay? I know the liquid is going to still beat the oven, okay? I know the liquid is going to beat the oven. Now, unless you broil it, so if you put to infinity to 550 for the oven, look what happens. It still cooks faster in the oil or the liquid, but the oven is not that far away from it. And you might say, oh, it's healthier than cooking it in oil. Okay? All right. With that, I'm going to stop. And we can continue next time. We'll discuss this a little bit more. But this is like just the baptism with ODEint, with fire. Okay? But you just solved an ODE. Now, go to your ODE class, take any ODE you're studying and just change the right-hand side over here. Take an initial value problem, change the right-hand side and see what happens. And you're going to be able to solve all of those problems with ODEint. Okay? All right. I did not ask for anyone to volunteer a tip today. So if anyone has a tip, please speak up. If not, Sophia and I were talking about a tip in the beginning of the class. So the tip is, when you schedule a time with someone, like don't tell them I'll meet you at 10:15. Tell them I'll meet you at 10:17. What happens then is that that's an awkward time. And then what it's going to do is going to trigger in the other person's brain a mechanism to stress them out. Like I have an appointment that I need to remember. It's not 10:15 or 10:30. It's 10:17, right? So they're more likely to actually remember it or write it down. I do this with my students, with everyone I know all the time. Like this class, if I were to schedule it at 10:47, I would do that, because then you're more likely to think like 10:47, it's a weird time. You know, nobody schedules a time at 10:47, okay? So, you know, try that next time. First, it will give the other person a giggle, like, you know, you're weird. Like, why would you say let's meet at 10:12? But do that, and they're more likely to be punctual, all right? Okay, everyone, have a nice day. Okay, I'll see you next week.